All right, let's get started. All right, so problem set 2 is out due end of this week. Any questions or problems? Yes?
In PS2, I believe, in the second portion of it, where we're looking at asymptotic rates, specifically for the equations that are very different to anything that we've seen in terms of say, how should we go about testing those two against each other to see which one is going to be the upper bound, which one is going to be the lower bound, which it's going to be?
Okay, so which one are you talking about here?
I believe part 2 with asymptotic notation.
PS2 too?
Yes. Oh, maybe it was the. Oh no, sorry, it was PS2 1.
Okay, so how do we go about testing what?
So, on the later questions,
Mhm.
they aren't higher order terms that we're used to seeing, I suppose. You're comparing things that are some base raised to a log n compared to something that we've already seen like n log n.
Okay.
And I guess I can't intuitively think about how I'm comparing those two functions to determine which one has the upper bound of the other.
Okay, like this one here?
Yeah.
Okay. What's the relationship between, okay, so for these in general, so there's that one, there's, here's, you're comparing base 9 to base 3 where the exponent's different. Here you're log of 3 to some power. Okay? In all of those, what they all have in common is you need to simplify them. You need to do some, use powers of logarithms or exponents to simplify them. So let's take this one in particular. What's the relationship between taking something to the second power, taking 2 to some power versus taking the log base 2 of something?
It's the log base 2 of it is going to be having it more than I can't.
Well, there's a simple word for the relationship between the exponentiation and taking the logarithm.
Right.
What's the relationship between those operations?
Inverse.
They're inverses.
Yeah.
So if you take 2 to the log base 2 of n, what do you get? If they're inverses.
Sorry, I get really flustered when I'm trying to think about it off the spot.
Okay, well, I'll let anyone answer. N. They're inverses. It's like doing, n times m divided by n. You get n out. So right there, that just simplifies to n. And now you're comparing n log n and n. So the idea is you need to simplify to something you know how to deal with. Any other questions? Mm-hmm.
Yeah, for number 7 on this one.
Yeah.
I tried doing the product rule breakdown thing. But when I do that, one of them, so it's big O and then little o, right? But I get big O and then omega.
Well, turn the omega around, you got a big O. I don't know what you have omega O.
It's like the other. It's like.
Well, all I'll say for this one is any positive power of n grows faster than any logarithm of n.
Yeah.
N to the 1 billionth grows faster than log of n.
Okay.
Leave it at that. You had a question back there.
I had a question on one of the problems on PS2-3.
Mm-hmm.
Question 4 or 5.
2, 3. 6.
Can we just set C to anything in this problem?
Yeah. You're allowed to use any C you want, but in a way that lets you use the smallest possible n null. You can't, well, let me change my answer. You can't pick a C. You need to find the smallest n null such that there's some C that'll work. So another way to think about it is there are lots of pairs of n null and C that will let you do the proof.
Yeah.
Of all those pairs, what's the smallest n null that shows up?
Okay. Thank you.
Mm-hmm. Yep.
Do you recommend we put these into a graphing calculator, or should we just get used to not having a graphing algorithms?
Yeah, I mean, I would recommend, for some of these, I'd recommend graphing them to look at them. Whether you use a graphing calculator or not is up to you. You won't be using one on the exam, though. But something like that, 6 isn't too hard just to sketch a picture, a rough picture. It's really all you need. Yeah?
Well, in question 8, and I believe the following questions are like this too, but there's, at one part of the question, it says like n naught is equal to n. Is that n different from like f of n or o of h of n?
I'm trying to remember this.
So it's like the same letter, and I kind of got thrown off by that.
Well, the thing is, you're asking about this n and m right here. Oh, it shows down here.
I'm just asking if that n is supposed to be some kind of constant, or is it referring to like the n is the problem size? Because they're like the same letter.
Yeah, no, I think this is again, these are particular n's and m's. They're unrelated to this n. Like, bad choice by me. Because they appear, I was looking, they didn't appear in the first question, but they appear here. So just imagine you've shown that, you used n naught equals 7 and n naught equals 9. Yeah, they're constants that you used in the proof. Thanks for pointing that out. Anything else?
Can you go to 2-2? And I think the last option you mentioned now.
So a different quiz.
Right.
Okay.
2-2.
Any, before I go back? No, I'm going back.
And
Question
question 9.
9?
Right. So the last choice, the generates a random integer k. That's the first one in your case. Does that always, like, every time it just gives a random number?
Yeah, it's a random number generator. Every time you call it, it
So it's just
calls a random number
not
generator.
even working for a cache table?
You don't have to explain the answer, but I'm just telling you that
Okay.
it's a random number generator. You might get 7 one time and 2 the next, and so forth. Anything else? Okay. Well, we already talked a bit about this. So we're moving to chapter 2 of the book, which is about divide and conquer algorithms. And it turns out, for reasons that we'll see, divide and conquer algorithms often involve logarithms. And in dealing with logarithms, it's nice to know some of their properties. So that's what this first slide here is about. And specifically, I say log base 2 of n, but I want to remind you that when you're using asymptotic complexity notation, like big O, the base of logarithm doesn't matter unless the logarithm appears as an exponent. Right, there's a difference between n to the log base 2 of something and n to the log base 3 of something, because it's an exponent. If it's in a position where the leading constant would be ignored, the base just amounts to a leading constant. So anything we say about log 2 here works for any other base. So the most fundamental thing is logarithm and exponential are inverses. If you take the log of the exponential, that's the same thing as taking the exponential of the log, it's the identity. So log base 2 of 2 to the n is the same thing as 2 to the log base 2 of n, which is the same thing as n. They're inverses. Exponentials grow really rapidly. Logarithms grow really slowly. Mirror images of each other. So that's one important thing to know. Another thing is, another way to think about it is log base 2 of n is the number of times you can divide something in half before you get to 1. So 16, 8, 4, 2, 1. You can divide that 4 times, and so the log is 4. It's roughly the number of bits needed to represent a number in binary. So right there we see that 14 is 1110. That's 4 bits. Log base 2 of 14 is roughly 4, between 3 and 4. It's very slowly growing. So these numbers, I encourage you just to remember, log base 2 of 1,000 is about 10. 1024 is 2 to the 10. So log base 2 of 1,000 is about 10. Of a million is about 20. Of a billion it's about 30. So some handy things to know. They grow very slowly. And it's possible to convert between bases. This calculation here shows converting log base 2 to log base 10, and the upshot is that let's see, the final thing I'm doing there is, I can't even read it. Log base 2, very end there. Log base 10 of 2. Or log base 2 of 10 is about 3. Anyway, there's a way to convert between bases. So we'll see a lot of logarithms. We'll also see a lot of recursion, because when you talk about divide and conquer, you're talking about recursion. You're talking about making recursive calls. And in fact, for the rest of the semester, we'll see lots of recursion. Almost everything we study is going to involve recursion in the end. So if you're the kind of student who didn't quite figure out recursion in 1410 and 2420 and have managed to avoid dealing with it until now, the chickens are coming home to roost. You've got to, you can't start thinking about recursion as some kind of weird thing. It's just fundamental. And let me try to help how to think about recursion. So here's an experiment. Here is a method. Is palindrome takes a string, and you can see what its specification says. Reports whether S is a palindrome, whether it reads the same forwards and backwards. But I want to focus on the implementation. Could someone describe to me how this implementation works? How does this implementation determine whether S is a palindrome? What does it do? What does the body of the method do? Yeah?
Turns the string around and then sees if it's the same as the original string.
Okay, right. Okay, succinctly put, it reverses the string and compares it to the original and sees if they're the same. Okay, would anyone describe it in any other way? All right, and in fact, that's how you might say that. Returns whether S and its reverse are equal. In particular, though, you would never say this. You wouldn't say, okay, this creates an empty string R. It iterates through S from left to right as it encounters each character C and appends at the beginning of R. Next, it iterates through S and R, comparing corresponding characters. If any are found that are not equal, returns false, otherwise returns true. What's wrong with that description? Yeah?
It's too verbose.
It's too verbose, it's too detailed, it's too low level. Where did those explanations come from? Where did I get the part about iterating through S from left to right? There's no loop there. Yeah?
Dot equals.
Sure. So one of the left to rights, I'm speculating about how dot equals works. In another part, I'm speculating about how reverse works. In other words, I'm not describing the implementation in terms of what these methods of the specification of reverse and equals. I am sort of folding their implementations into the description of that implementation. There's too much detail. And I don't think anybody thinks about is palindrome that way. You think about it as, okay, you reverse the string, however that happens, it just happens. I don't worry about how reverse works. I just reverse. And then I see if it's equal to the original. You don't get into how reverse and equals works. Okay, so that's a non-recursive method. Okay, here is merge sort. Could someone describe to me how this works? Yeah.
Take your array, split it in half, sort the two halves, put them together.
Okay. So he said you take the array, split it in half. Well, I guess we should deal with the if. If the array is small enough, if there's 0 or 1 elements, we do nothing. Otherwise, if it's 2 or more elements, we split the array in half, sort the two halves, and merge them. Okay? Anyone have a different explanation? Well, what do you think of that first explanation? Is that how you think about merge sort? Yeah?
Well, I guess what I would have emphasized is that you're breaking up the list over and over again until you get to very small pieces. Then you put them in order and merge it back together.
Okay, so he's saying that that the array is split over and over again until you get small pieces and you put them back together again. Okay? Anyone have a different way of describing it? Okay, so let's compare these two. I don't want to pick on anybody, but one of those explanations is the way I encourage you to think about it, and the other way isn't. So I'm glad we have both answers. You should approach it like that is palindrome method. If A has fewer than 2 methods, it does nothing. Okay, that's easy to see. Otherwise, it sorts the first half of A, it sorts the second half of A, and then it merges the two halves. That's what the code says. And that's the way you ought to think about it. What did we not get into here? Yeah?
What's going on?
We did not get into how merge works. We didn't speculate about how merge works. We didn't talk about, okay, merge is going to have a side array, an extra array, and it'll iterate through A, simultaneously through 2 pieces and compare and copy. We didn't get into that business. We just assumed we know what merge is. What else do we not get into?
Subsequent calls to sort.
We didn't talk about how those 2 recursive calls to sort works. We didn't say, we just said sorts the first half, sorts the second half. We didn't talk about how. It doesn't matter. We can see how sort works, what it does. It rearranges a range into ascending order. We just went by a specification, just like we did for reverse and equals on the previous slide. Okay? The way you shouldn't think about recursion is this way. Splits A into half and keeps doing that over and over again until the array has fewer than 2 elements. So, as you said. Then, as it returns from the recursion, merges the halves with each other. I mean, that's true in some sense. It's not worded particularly well. We know that over the course of recursion, the array gets smaller and smaller until it hits a base case. But when you think of recursion that way, you are making the error of describing how something works in terms of its implementation instead of in terms of its specification. Just because this is a recursive call doesn't mean you should peer into the implementation and think about how this call is going to work. You just assume it does what it says it does. It sorts. And if you're willing to do that, to think abstractly about recursion, the same way you think abstractly about any other method call you ever see, then recursion just becomes a kind of method call. But if you insist on treating, when you're trying to understand code, if you insist on treating sort differently than you treat merge, you're going to have trouble. No one's tempted to explain how this works by also explaining how merge works. So don't be tempted to explain how sort works by explaining how sort works. That's circular. It's understandable you get confused. You're explaining how something works in terms of itself. Explain how this works in terms of the specification up there. Now, if your goal is to understand what happens when this thing runs on a computer and on the stack, then it matters. You know, it is handy to know that the method's called over and over again, and the array gets smaller, and then as it returns, it merges. But if you're just trying to understand how it works at this level, just think abstractly. Think about every one of these method calls: sort, merge, in terms of their specification. And for sort, it's sitting right there. Okay, well, that's my pep talk on recursion. Any questions? Anything anybody would like to add? Okay. The first divide and conquer algorithm we're going to look at involves multiplying long integers, big integers. And so let's think about algorithms for adding. So on the left, we have what I call the grade school algorithm for adding numbers. So we're adding 149 and 926. And you know the algorithm. You take the first two digits, and implicitly there's a carry of 0 here. So you add 0, 9, and 6 and get 15. And then we sort of reflexively know is if this is a two-digit number, then that 5 there becomes the quotient, the sum we write there, and the 1 becomes the carry. But in fact, what we're doing is we're taking 15 mod 10 to get the piece of the sum, and we're doing 15 divided by 10 to get the 1 to carry. So to do this addition, it's 9 plus 6 plus 0 is 15. We compute the 5 and the 1. And then it's 1 plus 4 plus 2. That's 7. So we write the 7 and carry the 0. And then it's going to be 0 plus 1 plus 9 and so on. So that's grade school addition in base 10. Now, just to show you that this generalizes, suppose you have a base 10 calculator and you want to do the addition in base 8. What's the difference? Yeah?
You're just modding by 8.
Yeah, you're modding by a different base. We're still doing the additions in base 10. We can think about it as base 10. 5 plus 6 equals 11. We take that mod 8, we get 3. We carry a 1. So the algorithm is very robust with respect to what base we're working in. So that's grade school addition. Next thing we're going to think about is we're going to talk about algorithms. We want to be able to multiply really long numbers, like hundreds of digits long. And one thing we have to decide then is how can we represent such numbers that have lots of digits? Because the integers built into programming languages are relatively short in number of digits. Certainly don't contain hundreds of digits, unless if you're using Python. Python is an exception. Automatically, the big integers are the default. So this might be a way of asking what's going on inside Python to represent big integers, or what's going on in the big integer class in Java, and so on. So how can you do that? How could we represent arbitrary length integers? Suppose we had a big integer class, and we wanted to, what would be the representation? What would be the instance variables you'd need to represent an arbitrary length integers? Yep.
You could use a string.
A string of digits?
Yeah.
Okay. So strings can be arbitrarily long. So you can imagine using a string of 300 digits to represent a 300-digit number. That's one idea. Yeah?
An array of uint.
An array of what?
Of unsigned 8-bit integers.
Okay, unsigned 8-bit integers. So he's an array of bytes. Yeah?
How precise do we need to be with this thing? Because you could just use a number to store a power and say 10 to the 6 or something to get the size.
Well, I need to know all the digits, not just the size.
Okay.
Yeah. Got to be able to exactly represent integers. Okay, so far we got an array of bytes, and we got a string of digits. Yeah?
One of the things that we know, I'm guessing
we know that no matter what we choose, we can, well, if we use bytes, for example, we can figure out how many bytes we need by taking a log. Yeah?
Could use a linked list, that way you don't have to do array resizing.
Okay, so a linked list of what?
Digits.
Of digit characters. Okay. What else? Any other suggestions? Yeah?
We're expanding on that, we can use a skip list for performance.
Okay, so he's proposing a skip list, which is a data structure that you may or may not have heard of. Yeah?
What if we do it like scientific notation, except with logarithms? So we have to keep track of both the number and the base we're raising it to.
Yeah, you got to be, I'm a little worried when you got to be sure you don't have, you're not losing any precision. You got to these aren't floating point numbers, so they have to be represented exactly. Okay, yeah?
Maybe like a map where the like place of the digit in the number is the key, and then.
Okay, so a map that maps, 0 to the ones digit and 1 to the tens digit and 2 to the hundreds digit, something like that. Well, let's see. I have a list, string of digits, that's one possibility, something like that. An array of digits. How about just, instead of an array of digits, an array of integers? What would be the difference between that and the first one? Yeah?
At least from a programming perspective, you don't have to do any conversions from a string into integer.
Okay, so in both of these first two ones, we've got digits, but the code for the digit 5 is not 5. Right? The code for digit 5 is, I forget, but it's some 2-digit number. So there's a conversion to turn the character 5 into a number that we can actually use. Whereas here we've actually got the 5. So that's the argument against actually using characters. Let's use actual numbers, and there's a conversion step that we don't have to do every time we multiply things or add things. Why not use base 2? Why not an array of integers in base 2? Why should we use array of integers where the base is 10? Yeah?
Are we doing base 10 math? Or just another
Well, we're doing base 10 math, but the computer does base 2 math. All right? Computer manages to do base, if we use base 10, yeah, it's going to be done with ones and zeros. Yeah?
For really big integers, that's going to take up a lot of space.
Okay, right. The array is going to be about 3 times longer than in base 10. Right? So what would be a good base to use? Yeah.
Well, I'm curious, would it be longer, like, if you made it so that way as it goes forward, it doubles as binary does, like you represent it in binary digits?
Yeah, if you take an integer, representing it in base 10 takes about log base 10 of that number of digits. Doing it in base 2 takes log base 2 of that. And the difference is a factor of 3 point something. Yeah?
So is it worth putting in base 16 because that's easy to convert to base 2?
Okay. Base 16 looks nice because it's shorter. Now, before we go any farther, what's the advantage of having a shorter array? Imagine you're trying to add 2 numbers and they're representing in base 2. So you got a bunch of ones and zeros. Okay, what's your algorithm going to look like? You're going to iterate through the array from the low end to the high end, the 2 arrays, and add the corresponding pairs of bits. Not bits, they're actually integers, they're ints. So you'd be adding 1 and 0 and getting 1, or 1 and 1 and getting a 0, carry the 1, and so on. Okay, so your loop runs a long time. If we use base 10, now we're adding 9s and 8s and 6s and such, and it takes less time because about 3 times faster. Use base 16, it's faster still. Yeah?
One of the things we have to consider is that on a hardware level, like down at the processor level, they have all kinds of implementations that speed up addition, so you don't just go through bit by bit. You actually group them together in groups. That's one of the things we can try to put into our algorithm.
Well, yes, but let let me ask you this. We got a processor that's able to deal with, say, 64-bit integers. So it can add two 64-bit integers or multiply two 64-bit integers in one cycle. Certainly add them. And then suppose we use this powerful 64-bit processor to add pairs of numbers represented with ones and zeros. Okay? How much of that circuitry are we actually exploiting each time through the loop to add ones and zeros together? Almost none of it. We're wasting virtually all the power of the ALU every time we add ones and zeros together. Now, when we're adding bigger integers together, we're using more of the power, but still, with 16-bit integers, we're still just barely scratching the surface of what it can do. Yeah.
Why don't we use the base equivalent to the largest integer we can represent?
Okay. No, that's getting at it. Let's make the base bigger. So bigger is better because there's fewer additions to use, and the reason we get away we get away with fewer additions because we're using more and more of the power of the processor. You know, like in that first case with the array of ones and zeros, not the first case, the fourth one. The way it looks to the computer is going to be 63 zeros followed by a 1 plus 64 zeros. We're asking it to do that kind of math for us. Let's not make all the leading bits be 0 on these things. So the key question is what base? So the base is, the bigger the base, the better. But we don't want the base to be too big because we're going to need to, whatever we store in these arrays, we're going to have to be able to multiply and add, I'll call them digits. We have to multiply and add the individual entries in the array. So what problem can we have if the numbers in those arrays get too big? What could go wrong when multiplying and adding? Yeah? An overflow. So what's the biggest, suppose we have a 64-bit machine. What's the biggest number we can put in one of those arrays to avoid overflow on addition and multiplication? Yeah?
It'd be the square root of the max end.
Right. Be the square root of the maximum integer. Because anything bigger will overflow the maximum integer. So the maximum integer is like 2 to the 64 minus 1. It's assuming unsigned. So the biggest integer we should have is about 2 to the 32. So that's the base we'll use, 2 to the 32. Base 2 to the 32. There are 2 to the 32 digits in that, not digits in quotes. Digits is a base 10 thing. There are 2 to 32 things. 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 2 to 32 minus 1. Oh, and there's this one last thing. Division and mod operators need to be fast. Why is that? Where do we do division and mod? Yeah?
Well, that's how you do the addition that we were going over before.
Right. To do the addition, we had to mod by the base and divide by the base. So it's convenient if our base is a power of 2. Because with powers of 2, if it's power 2, then we're just doing bit shifting and bit masking to do these mods and divisions. They're not very complicated. So let's use base 2 to 32. So every digit will fit into a 32-bit integer, and then when we multiply them, we won't have bigger than a 64-bit integer, which the computer can deal with. Now, if you actually look at it, if we take our huge number, write it in base 32, 2 to 32, where every digit is a 32-bit integer, if you wrote all those numbers together in an array, what would you see? What would it look like? Yeah?
Would it be something like hex, where after 10 or 9 it starts switching things?
Okay, well, let me put it another way. Let's suppose we put each of these digits, what I'm calling digits, suppose we wrote them in base 2. That's how they'll be stored in the computer. You'll have an array of 32-bit integers in binary. If you string them all together, what will you have? The original number in binary. All we're talking about doing is taking the binary representation of our huge number, chopping it up into 32-bit segments, and storing each segment in an array element. That's in the bottom. In the end, that's all we're doing. So, no big deal. So this just makes arguments already made. Each digit will fit in a 32-bit integer. We can do 64-bit arithmetic, and we will not overflow. This shows you why. And div can be done if we have to take, when we have to do div the base, we just discard the low 32 bits of the result. Now this shows you base 8, not base 2 to 32. And mod can be done by discarding all except the low 32 bits. So we can div and mod quickly. So that's basically how big integers are represented. Just lists, arrays, whatever, of chunks of bits. Okay, so we got that. We assume we have some way of representing big integers. What then is the complexity of adding two n-bit integers? So you have to adjust your thinking. You're used to thinking, okay, addition happens in constant time. Why do we say that a lot? Why do we say things like we can compare two integers in constant time, or we can add them in constant time, or multiply them in constant time? Yeah?
Yes, because it's a trivial operation for the processors. We just assume that addition, since it will run on one cycle.
Okay. Yeah, it is done in constant time. If the numbers are not too big, if they're that's what a processor does. It adds things in constant time. But when we start talking about arbitrary length integers, we have to adjust our thinking. Now the amount of time it takes to add two big integers together depends on their length, just as the time it takes to sort a list depends on its length. So we'll use base 10 here because it's just easier for us to cope with. What would you say about the complexity of adding two n-bit integers? Yeah?
Well, with our previous algorithm, we went right-hand and compared top and bottom one digit at a time. So effectively, that's 2n, or complexity n, because
Yeah.
we're comparing each digit.
Okay, so it's linear. If you have 3 digits, you have to do three. You have to add 3 pairs of digits. If you have 1,000 digits, you're doing 1,000 adds, 1,000 machine adds. So the amount of work you do is proportional to the length of the numbers you're adding. And I want to urge you to be careful when we're talking about complexity. We've always got to be talking about it in terms of the length of the inputs. So that's why we talk about the number of bits or the number of digits in the number, not the number themselves. We don't ask what's the complexity of adding x plus y. We ask what's the complexity of adding an n-bit number and an m-bit number. Now, do I have to be careful about whether I'm talking about bits or digits when I talk about the length of a number? Does that matter? What do you think?
If they're represented the same way, it should be scalable. So I think it doesn't make a huge difference. One would just be a constant to the other.
Okay, so right. So if you compare the complexity of adding two numbers that consist of a bunch of bits, and you also talk about the complexity of representing numbers that consist of a bunch of digits, the time complexity is going to be different by a factor of 3. It's just a leading constant. Because in the end, you're adding two numbers. Their length in bits is log base 2. Their length in digits is log base 10. Their length, the way we just discussed about representing it against, is log base 2 of 32. They all just differ by a leading constant. So digits, bits are equally good measures of the length of a number when you're talking about time complexity. Okay, so grade school is linear. What about multiplication? Grade school multiplication. How many operations required to multiply a pair of n-bit integers? Yeah?
Is it n squared?
That's n squared, because we got to take the 6 and do 1, 2, 3 multiplications, and then we got to do 1, 2, 3 multiplications, and then we got to do 1, 2, 3. So that's 9 multiplications. Plus there's some additions down here, a linear number of additions. But what it boils down to is it's n squared. So grade school multiplication is n squared. And you know that intuitively. It's a lot easier to add than to multiply. Yeah?
So what if you have like a different length of a number on only one of them? So if you have like a 4-digit number times a 3-digit number.
Okay, so if you've got an n-bit integer and an m-bit integer,
Yeah.
what do you think? I mean, that's you know, two variables there. We don't see that very often. At least we haven't seen it yet in the course. How would you express complexity there? The lengths are not the same. Yeah, it's O of n times m.
Okay.
Is the number of operations, of machine level operations we'd be doing. Okay. All right, so let's put it all together. We've talked about recursion. We've talked about algorithms for techniques for representing numbers, integers. Let's see if we're going to look at a recursive multiplication algorithm here. The idea is it'd be nice if we could multiply faster than quadratic. Okay? There's some famous algorithms, particular public key encryption, that depend on being able to multiply quickly. And let's see if we can speed up, get away from n-squared multiplication. If that's the only way you've ever thought of doing multiplication, then it may seem you can't possibly do it faster because there's only one way to do it. But in fact, you can. Let's see if this way will give us a better way. So this is our first divide and conquer algorithm we're looking at. So what we're going to do is, as you often do, well, as you always do in divide and conquer, is you divide the input into pieces. In this case, we're going to split the input into halves. So we're going to take x and split it into its first n over 2 bits and its last n over 2 bits. And we could reconstruct x. So xl is the left half, xr is the right half. And that's just reconstruct x by taking x of l, multiplying by 2 to the n over 2, and adding x of r. Or another way, take x of l, bit shift it, n over 2 bits, and then plug in x of r. That's assuming n is even. You know, we could deal with odd n's. It just complicates the discussion, doesn't add anything to it. So we'll just assume everything works out well. So we'll do that split, Okay, with me so far? Dividing big old number into its first half and its second half. Two numbers like that. So we've got 4 numbers now. And the idea is to, let's look at what x times y would look like if we expanded it out this way. So x times y is equal to that product right there. And rearranging that product right there. And that's my algorithm. So what is the recursive multiplication algorithm here? How would you describe it? Where's the recursion? Yeah?
Is it in the multiplication between the left and right hand sides?
Right. So x times y is being described in terms of xl times yl, xl times yr, xr times yl, and xr times yr. So there's 1, 2, 3, 4 recursive multiplications happening. But each of those multiplications involves numbers that are half as big as the original. There's some other stuff though. In addition to those 4 multiplications, we have to do this addition. That's one thing. We have to do this, which looks nasty. It's 2 to the n over 2 times that. But really, this is pretty simple. How would you do this? 2 to the n over 2 times that sum. Yeah, it's just a bit shift. You just throw n over 2 zeros at the end, and you're done. It's like multiplying by 1,000. You just put 3 zeros at the end, multiply by 1,000 in base 10. So it's just a bit shift. That's linear time. So we do a bit shift, we do an addition, and addition. So 3 additions and 2 bit shifts will get it done for us. In addition to these 4 multiplications of numbers half as big. And the question is, does this pay off? Is this any faster than just multiplying x and y the old-fashioned way? That's what we're going to explore here. Try to figure out. So let me just illustrate this, and I'm going to use base 10 now instead of base 2. The same idea. We split the numbers in half. We've got to compute those 4 products. So, and this is what it works down to. 10 squared times 2 times 5 plus 10 times 2 times 1 plus 3 times 5 plus 3 times 1. So we turned it into, we're doing, that's one recursive multiplication there. There's 1, and there's 1. This one right here is not really recursive multiplication. This is a digit shift. So that's just doing the recursive multiplications. It's 10 squared times 10 and so on. We simplify a little bit, do the digit shifts, and add. And that turns out to be the right answer. So that is a recursive multiplication algorithm using the divide and conquer idea. Split the numbers in half, give you 4 numbers, do 4 multiplications, combine the results to get the original answer. And the question is, what's the complexity of this thing? Is it better or worse or possibly the same as grade school multiplication? How would you figure this out? Yeah.
So we know that with each iteration we're cutting the number in half, and that's pretty logarithmic, and then we know at each step we're doing addition, which we learned is a linear operation.
Mm-hmm.
So just based on those two things, we know that we're doing a linear operation for every iteration, which we know is logarithmic, so we need to be n log n.
Okay, so he's speculating n log n. That would be nice. That'd be certainly faster than n squared. And he's just, it sounds like he's sort of pulling on his intuition about, say, how merge sort works. But what's the difference between this and merge sort? Merge sort, you split something in half and then do 2 recursive operations. Here, though, we're splitting things in half and doing 4 recursive multiplications. So there's some difference there, but you may be right. Yeah?
As written, it doesn't seem like you gain much, because each of those is n over 2 squared.
Uh-huh.
And so you're just getting n over 4 squared times 4.
Okay, so there's another intuition. All right? That's, yeah.
In terms of the new one, we have, it's like 3 variables. It's 2 times 5, and then 3 times 1, and then 2 times 1 plus 2 times 5. But if you do it the other way, then you have 4 plus versus. So each time that you multiply, instead of doing 2 times 5.
Right. So we can sort of look at the number of digits being multiplied and see how that compares. Let's go at it systematically. Let's just count things. So I just made a list of what we're doing. We're doing 2 splits of n-bit integers into pairs of n over 2-bit integers. We do 4 recursive multiplications. We do some additions and additional, and then some bit shifting. Multiplication by powers of 2 or bit shifting. So that's our list of all the operations that go into doing this recursive multiplication. And the list is at the top now. And let's think of the complexity of it. So I say that the splits can be done in linear time. Okay? So if you have a whole bunch of bits and you need to split, well, what do? You take the whole thing. If you replace all the high bits with zeros, that's one of the splits. And if you replace all the low bits with 0 and then shift them off, or just forget about the zeros, just shift to the right, that's another split. So the splitting just is proportional to the number of bits. So that's linear time. I don't know what the cost of those recursive calls are. That's what we're trying to figure out. All these additions, 3 cases of addition, are linear. We already saw that. And the multiplications by powers of 2 are bit shifting. So that's linear. So what could you say about the cost at this point? The cost of multiplying 2 n-bit integers. What's it at least going to be? It's going to be omega of n. It's going to take at least linear time. Now, this is very typical of what happens when you analyze a divide and conquer algorithm. You end up with the cost of the algorithm is going to be the cost of the recursive calls plus the cost of everything else. And the cost of everything else is usually pretty easy to get. So in this case, the cost of everything else is O of n. But there's still the 4 recursive calls, which I don't know how to consider them. So this is what I'm going to say. I'm going to let t of n be the time required to multiply 2 n-bit integers. And so imagine we had this function t of n. I claim t of n would be equal to the time required for the four recursive calls plus the other time. Hard to argue with that. What is the time required for the four recursive calls? It's 4 times t of n over 2. T of n over 2. If we got this hand, we're postulating this function t exists. It tells us how long it takes to multiply 2 n-bit integers. So t of n over 2 must be the time it takes to multiply 2 n over 2 bit integers. We're doing that 4 times. So this is the cost of the recursion. And this is the overhead, the cost of everything other than the recursion. And also, we know that the time it takes to multiply 1-bit numbers, we didn't show the base case, but multiplying 1-bit numbers is going to be easy. That's just going to be constant time. So that's called a recurrence relation. And here it is written out up there. So t of n is 4 times t of n over 2 plus O of n. T of 1 is 1. And now we've reduced our problem to trying to put a bound on that. It'd be nice to solve the recurrence and come up with a formula for t, but we can't solve it exactly because that O of n right there is hiding too much information. We don't know the exact values of what that O of n stands for. So what we want to do is put a big O bound on t of n. And since that t of n is the running time of our algorithm, a big O bound on t of n is going to be a big O bound on recursive multiplication. Just like we saw in the last 2 weeks, we saw that analyzing iterative algorithms like insertion sort, selection sort involves summations because you've got nested loops, so you do summations. Analyzing divide and conquer algorithms usually involves recurrence relations. And the ones we'll look at are always of this form. There's going to be one term here that deals with the recursion. What's the 4 mean? What if this said 3 instead of 4? What would that tell you? 3 recursive calls. Okay, and this 2 is because we're dividing it in half. If we're dividing, if we're cutting down, cutting it to a quarter of its original size, it'd be a 4 here. This is just a measure of how much work it takes to do everything else but the recursion. And the base case is always going to be constant for everything we look at. So what we've got to do is figure out how to deal with recurrence relations. And then once we know how to deal with recurrence relations, we can come back and solve this one and see how good or how bad that recursive multiplication algorithm is. Let's take a break and we'll see how to do that. Okay, so what I'm going to do to, I'm going to show you a way to solve recurrence relations, and we're going to approach it by looking at a variety of divide and conquer algorithms. And my focus isn't so much on the algorithms, but how we analyze it. So first we're going to look at a strange algorithm called copying binary search. So you got a sorted array, you're looking for an element in it using binary search. We're going to do it recursively. Normally you would just do this iteratively. And furthermore, just to make my example work out the way I want it to, before we search it, each level recursion, we're going to copy the array. There's no reason whatsoever to copy the array. It just suits my purposes better. And then we're going to, we want to analyze it and see what the recurrence relation is for it. So this is sort of practice with creating recurrence relations. So the cost, the time required to run this thing for a given array is going to be, we're going to have to, we do a probe to the middle, decide, we're looking at the worst case, so we're going to assume we didn't find it right away. We've got to figure out which half the array to search, and we've got to do it recursively. So what's the overhead? What's the stuff we have to do at each level of recursion? So just think of, the way to do this is just think at the top level. What's the overhead? What do we have to do before and after the recursive call? Yeah.
We have to copy the half of the array, which is ordered.
Okay, so we have to copy half of the array. What else do we have to do? Hence, the answer is up there, by the way. Yeah?
Have to do like some if statements.
Yeah, so there's the comparison and the if statement that determines what you're going to do. So basically everything you see here, well, that's the base case. Everything, this division you have to do, you have to do one or two of these comparisons, and then before you make the recursive call, you have to do the copy. That's the overhead. And I wrote that in yellow. So the cost of this overhead is, as one of you observed, is O of n. It's the copying is the expensive part. The other stuff's constant. So we got O of n overhead. And then we got to recursively search one n over 2 element array. So what would you say is the recurrence relation? What's T of n? It's always going to be of the form, first of all, there's going to be an integer, which is the number of recursive calls. What will that number be? Okay, I heard a 2, I heard a 1. Now here's the thing. You look here and you see 2 recursive calls. So you might be tempted to say 2 recursive calls. But what's the catch? You're only going to make one of them because they're showing up in an if statement. This isn't like merge sort where you do both. You do one or the other. But a lot of students get confused because they want to say, okay, this is going to make a recursive call, and then that'll make a recursive call, and then that'll make a recursive call all down the line. That's not the question. The question is just look at the code. How many recursive calls get made? In this case, it's 1. So our light blue number is the 1. And the array is half as big each time. Okay? So there's the recurrence relation. 1 times T of n over 2 plus O of n is the recurrence relation. And if we could put a big O bound on that, we'd have a big O bound on copying binary search. Now, what if we changed the rules here and we didn't do the copy? We'd have to add an extra parameter to say, sort of give the low and high bounds of what to search. But we get rid of the copying. How would that change the recurrence relation? What's that?
Instead of adding big O of n, it'd be big O of 1 because we're getting rid of a copy.
Right. The yellow thing down there would be O of 1 instead of O of n. And if we could put a bound on that recurrence, then we would have the we could have a big O bound on that binary search algorithm. Okay? So you see I've got it color-coded here. And we'll be consistent with it throughout. Any questions about that? So this is skill number 1. Given an algorithm, can you come up with a recurrence relation for it? And then the other skill is, given a recurrence relation, can you put a big O bound on it? But the real skill is, given a problem, can you devise a divide and conquer algorithm for it? But we're not really doing that today. Let's look at, let's try to deal with that recurrence by looking at what's going on. So we're at the top level. We're searching in an array of length n. And how much work do we do? Forget about the recursion, the cost of recursion. How much work do we do? We already said it. What's the major component of the work? Yeah?
Copying, so n over 2.
Copying, right. I guess my animation doesn't show that yet. So anyway, we make one, so now we're down one level in recursion. There we got an array of length n over 2. The next level of recursion, we're n over 4. What about at the kth level of recursion? What will the size of the array be? So up here it was sort of n divided by 2 to the 0. Here it's n divided by 2 to the 1. N divided by 2 to the 2. So it must be n divided by 2 to the k here. But I don't show it. Okay, I forgot my slides. How much work do we do at this level? We already said n over 2. How much work at this level do the copying? N over 4. N over 8. And what about the kth level?
N over 2 to the k plus 1.
Right, n over 2 to the k plus 1. And I just get that by looking how this is progressing. This is 2 to the 1, 2 to the 2, 2 to the 3. So everywhere the exponent's 1 bigger than the level. So n divided by 2 to the k plus 1. Now the very last level is level log 2 of n. Why is that? Right, that's how many times you can divide the array of length n in half before you've only got one element. And the work we do at that level is 1. That's the base case. So what we got to do is add it all up. So what's it add up to? Let's see. Base case is 1. All the recursive case added together are 1/2 n plus 1/4 n plus 1/8 n plus 1/16. And that series, 1/2 plus 1/4 plus 1/8, in the limit converges to 1. So anyway, it's going to be less than n. So the whole thing is O of n. So this is a case where the top level alone was O of n. So if we could, recognize this is the kind of recurrence we're looking at, we could just figure out the complexity of the top level and be done. So copying binary search is O of n. Okay? Here's our recursive multiplication algorithm. Split the numbers in half, recursive multiply, add, bit shift the products. We already know the recurrence. We worked that out before. Let's follow the same idea and see if we can figure it out. So I'm just showing one of the pairs of numbers we're multiplying, assuming they're both the same length. So we got that. What's it going to look like at the next level of recursion? Imagine the recursion tree. At the top level, you're multiplying n-bit numbers. At the next level, we're multiplying n over 2-bit numbers, but how many do we multiply at the next level of recursion? How many recursive calls are there? 4. So we're doing 4 pairs of multiplications of n over 2-bit numbers. How many total recursive calls will there be to level 2? 16, 4 for each of those. So you can see this is a different animal. It's sort of exploding on us a bit. So how much work at the top level? How much overhead at the top level? Level 0. You said the overhead was linear, right? So we'll say 1n. Okay? What's the total work done at level 1? Right, add up those n over 2s, you got 2n. I'm writing it that way for a reason you'll see shortly. 4n divided by 2. 4 times each of the recursive calls. What about this level? 16n over 4. What about the kth level? Let's see, we went from 1 to 4 to 16, and we went from n divided by 1 to n divided by 2 to n divided by 4. So what should level k be? What's the coefficient? Looks like the powers of 4 here. Yeah? 4 to the k times n divided by 2 to the k. Okay? Then we get down to the base case. How many base cases are there? How many times do we hit the base case in this recursion tree? Let's see. Yeah, 4 to the power log 2 of n. Now, where that came from is over here. So at level 0, we got 4 to the 0 boxes. At this level, 4 to the 1 boxes, 4 to the 2 boxes. At this level, 4 to the k. So at this level, it will be 4 to that power. 4 to the log base 2 of n. Let's add it all up. 4 to the log base 2 of n turns out to be n squared if you do some simplifications. So we're doing, add it up over every, we hit the base case a whole bunch of times. Add all those up, we're doing n squared work. The rest of it, if we add up all the other levels, we get this. And that series, 1 plus 2 plus 4, that's powers of 2. And so we know that the sum of the first k powers of 2 is 1 less than the next power of 2. So we get that. And 2 to the log base 2 of n is what? N. So that's O of n squared. Turns out the base case is alone O of n squared. That's sort of the opposite of the other one. So this one, we do most of our work at the bottom. Even though that work happens really fast, there's just a tremendous amount of them to do. So O of n squared. Bummer, right? Remember recursive multiplication? We were supposed to improve on the grade school algorithm. Apparently we didn't. Merge sort. What's the recurrence for merge sort going to be? So T of n is going to be the time required to do merge sort on an n-element array. And put it together from these pieces up here. So 2 recursive calls, because both of them have to be made. There's no if. How big are the recursive calls? N over 2. And what's the overhead? That's the yellow stuff. Split the array into 2 halves, merge the 2 halves into a sorted whole. Well, the merge is the expensive part. Merge is a linear time operation. So what would be my recurrence? T of n equals what? Yeah?
2 times t of n over 2 plus some of the order n.
Right. 2 recursive calls. So just read it off. 2 recursive calls, each of size n over 2, plus a linear amount of overhead. And the base case is constant, as always. There's our recurrence. Okay? Once you have recurrence, we can do our analysis again. Let's do it. At the top level, we're merge sorting an array of length n. What about at the, we're going to make 2 recursive calls. How big will the array be at that level? Be 2 arrays of n over 2 being sorted. The next level, 4 of n over 4. Okay, at the top level, the merge is linear work, so I'm going to say 1 times n. What about at the next level? We're doing 2 merges, each n over 2. So that's 2 times n divided by 2. What about the next level? 4n divided by 4. What about the kth level? It's 2 to the k n divided by 2 to the k. And then what about how many base cases will there be? Same as before. It's good, except it's 2 to the log base 2 of n this time. That's just how the tree expands out. Add them all together. Well, the base case is 2 to the log base 2 of n, which is n, we know. What about the other? How do we do the recursive one? What's the amount of work we're doing at each level of the recursion? Yeah. These all simplify to n. N, 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 n. How many levels can there be? We're dividing n by half till we hit the base case. So how many times can we do that? Log base 2. So there's log n levels. Each level we're doing n work. It's n log n. So it's O of n log n. And each level of the recursion is contributing equally to the complexity. So that's the right answer. We're expecting to see n log n. Okay, so now, right about now, you're probably thinking, man, I'm not looking forward to doing this kind of analysis for divide and conquer algorithms. But here's the good news. Other people have come before you and said the same thing, and have observed what we've seen. I'm about to show you something called the master theorem. The master theorem is basically a recipe for solving the types of recurrences that happen when there are divide and conquer algorithms. And the master theorem has 3 cases. And those 3 cases correspond to the 3 types of recurrences we've already seen. And you won't have to do this. You will be able to use the master theorem. So here it is. This is just setting up what we've already done. We've got the master theorem can be used to solve recurrences of this form. So the idea is this is the number of recursions. This 1 over, we're basically multiplying n by 1 over b. So 1 over b is the amount by which the problem size decreases. And then O of n to the d is the overhead, the setting up and the combining when you're done. So we've got A, we've got B, we've got D. Those are the 3 numbers that determine, that go into using the master theorem. And there's how you use it. There's some restrictions. You have to have at least 1 recursion, so A is greater than 0. B has to be greater than 1. What would happen if B was less than 1? The problem gets bigger as you make recursive calls. That's no good. And then D has to be non-negative, so n to the D. And we got 3 cases, depending on whether we're always comparing D to log base B of A. And depending on whether that's greater than, equal to, or less than, we read our answer off here. Master theorem. So let's try this out. There's copying binary search. There's the recurrence. And by the way, we're assuming all through this that t of 1 is 1. What's A?
1.
Yeah, A is 1 in this case. What is B? 2. What is D? 1. It's end of the 1. Very good. Now we have to look at log base B of A. So what is the log base 2 of 1? To what power must you raise 2 to get 1? 0. Okay? Now, you need to learn how to do very simple logarithms in your head. You do not have to use a calculator to figure out the log base 2 of 1. Remember, when I ask you what's the log base 2 of 1, I'm asking you to what power must you raise 2 to get 1? 0. Right? No other power will do. So log base B of A is 0. Now we compare D and 0. D is greater than log base B of A. So we're up in this first case. And our answer is what? What's the bound on that recurrence right there? O of n to the 1, or O of n. Okay? So that's how you can solve, you can figure out how complex your divide and conquer algorithms are by applying the master theorem. Let's try this again. Merge sort. What's A? 2. B is 2. So the A comes from right here. The B comes from here. Be careful. Okay? Sometimes, what if it said 3n divided by 2? It would be 2 over 3. So the way to do it is you're multiplying n by a half. You take the reciprocal of the thing you're multiplying n by. N times 1/2, you take the reciprocal, you get 2 for B. If it was 3n divided by, or 2n divided, okay, I don't know what I said before, but if it was 2n divided by 3, it would be 3 halves. Yeah. Okay, what's D? 1. Log base 2 of 2. To what power must you raise 2 to get 2? That's pretty easy. D and the log are the same, so we're in the last case, or the middle case here. And so our answer is n to the d, but d is 1, so it's n log n. Recursive multiplication. A is 4, B is 2, D is 1. Power to which you must raise 2 to get 4 is 2. 2 is bigger than 1, so we're in the last case. So our answer is O of n to that power, which was 2. O to the n squared. Okay? That's not hard. Just the right amount of time, though. Now, I just want to tell you where the recurrence relation comes from. Don't leave yet. So, in this case, copying binary search corresponded to the case where d is greater than log base b of a. I just showed you that. For merge sort, it corresponded to that case. Recursive multiplication corresponded to that case. So we looked at examples of all three cases. How do you suppose you would come up with the master theorem from scratch? You would just analyze the general case. So what you do is you say, okay, we have some starting size of n. Each time we chop it down by a factor of 1 over b, and there's a different versions, and so on. You would just imagine a general case. You take the general case of the recurrence of the master theorem. You would work out just like we did. You would come up with sums down here for base case work and recursive case work. You would then try to simplify those sums for base case work, and it turns out that, for recursive case, that doing this sum right here depends on which case you're in, and you come up with the master theorem. So I'm not going to hold you to this proof of the recurrence relation. I just put it there so you can see, you sort of saw where it came from. We analyzed the three cases separately, but we didn't do it symbolically. So we will continue next time by doing more divide and conquer.
I was wondering if you could just go back to the recursive multiplication example.
Yeah, let me.